Symmetry. It's one of nature's most striking features. From the wings of a butterfly to the grace flight of a bird, symmetry is everywhere. A perfect balance between left and right, providing stability and harmony in motion. Humans have long admired this order. We see it in art, architecture, and even in our own faces. And when we began to fly, we followed nature's example. Early aircraft designs mirrored the symmetry of birds. Two wings extending evenly from the fuselage, each balancing the other, keeping the craft steady and controllable. Symmetry became a cornerstone of aeronautical design, a rule so fundamental that it seemed unbreakable. But as technology advanced, as engines became stronger and our ambitions reached beyond the speed of sound, that perfect symmetry started to look limiting. Throughout aviation history, engineers have experimented endlessly with the geometry of wings. Early biplanes used long, flat wings for maximum lift and stability at low speeds. Later, as flight reached higher altitudes and faster velocities, new forms emerged. Most commonly used for commercial planes are the swept wings. Then there are delta wings for high speeds as needed for military jets, and even forward swept wings experimenting with airflow and stall behavior. Each type designed for a specific aerodynamic challenge. At low speeds, aircraft benefit from long, straight wings. They generate high lift and allow smooth airflow, ideal for takeoff, landing, or endurance flight. But as airspeed increases, those same wings create a problem. When air flows over a wing, it accelerates along its surface. If the aircraft approaches the speed of sound, parts of that airflow can actually exceed Mach 1, forming local shockwaves. These shockwaves cause turbulence, wave drag, and even a loss of lift, long before the aircraft itself becomes supersonic. This limit is known as the critical Mach number, and crossing it can cause violent aerodynamic effects. Airflow separation, controlled surface buffeting, and in extreme cases also a total loss of maneuverability. To delay these effects, engineers began sweeping wings backward. A swept wing reduces the component of airflow perpendicular to the leading edge, reducing wave drag, allowing aircrafts to fly faster before shockwaves appear. But that improvement comes at a price. Swept wings produce less lift at low speeds, making takeoffs and landings more difficult. Hence, the ideal wing for subsonic flight performs poorly at supersonic speeds, and the ideal wing for supersonic flight performs poorly at subsonic speeds. To overcome this contradiction, engineers in the 1950s and 60s proposed a bold idea: the variable sweep wing. One would have both long, straight wings for takeoff and landing and sharply swept wings for high-speed flight. This variable geometry could, in theory, give an aircraft the best of both worlds. At low speeds, wings would extend outward, providing maximum lift. Then, as the aircraft accelerated, they would sweep backward, reducing drag and increasing the critical Mach number, allowing for high-speed flight. The concept worked spectacularly in some cases. Aircraft as, for example, the Grumman F-14 Tomcat, the General Dynamics F-111 Aardvark, the Mikoyan MiG-27, and the Panavia 200 Tornado all used the variable sweep wing to master both slow speed and supersonic regimes. For combat jets, where performance across a wide speed range is essential, this was a revolutionary step. But this elegant mechanical solution came with heavy compromises. Moving the wings shifted the aircraft's center of gravity, changing the pitching moment, requiring constant trim corrections. This forced designers to install stabilizers and complex balancing systems to keep the aircraft controllable. Additionally, the massive pivot joints that allowed the wings to rotate endured enormous bending and torsional forces. These joints were heavy, maintenance-intensive, and structurally vulnerable. Each movement also changed how the aircraft handled, adding mechanical complexity and pilot workload. supersonic bombers and fighters, the benefits outweighed the costs. But for civil or long-range transport, the variable sweep system proved too complicated, too heavy, and in general too inefficient. In 1958, at NASA's MS Research Center, aerodynamicist Robert T. Jones asked a daring question. What if a wing didn't sweep backwards symmetrically at all? What if, instead, a single wing pivoted diagonally across the fuselage? One side swept forward, the other backward. Jones called it the oblique wing. This idea was first discussed during the Second World War by German aerodynamicists. A single rotating wing relative to the fuselage. Even prototypes with the Blohm & Voss P202 and the Messerschmitt Me P1109 were under development but were never able to finish, as with the end of the Second World War, these projects were discontinued. The respective documents fell into the hands of the Allies, where the idea again was picked up by the United States, which brings us back to Jones. To most engineers, the idea looked bizarre, even unstable, but Jones saw elegance in asymmetry. He stated that the oblique wing would act like a variable sweep design, but without the penalties of mass imbalance. By pivoting one continuous wing around the central joint, an aircraft could smoothly transition between efficient low-speed flight and low-drag supersonic cruise, all while maintaining a nearly constant center of gravity. At low speeds, the wing would be perpendicular, generating maximum lift. As velocity increased, it would rotate, spreading the lift and volume along the fuselage. This, Jones predicted, would reduce wave drag dramatically and provide optimum efficiency at all Mach numbers. The central force behind this development is the so-called Whitecomb area rule, which describes the ideal cross-sectional area distribution along the complete airframe to reduce wave drag within the transonic regime of 0.75 and 1.2 Mach. The smoother the distribution from nose to tail, the lower the resulting drag. Now, at the example of the Convair F102 Delta Dagger, we see the initial cross-sectional area distribution of the aircraft's first version compared to the ideal distribution. Here, the steep rises and drops in area as the delta wing increases in width would have resulted in high wave drag as it deviates from the ideal distribution too much. Instead, engineers redesigned the aircraft. To conform to the area rule, they decreased the width of the fuselage with the length of the aircraft, which now gives us this cross-sectional area. This change resulted in less wave drag but also increased the plane's top speed. Now, in case of the oblique wing, the configuration naturally distributes the cross-sectional area more evenly across the length of the plane, reducing peaks and throughs in that area curve. The result? Less wave drag. Jones calculated that compared to a conventional symmetric swept wing, the oblique wing could reduce wave drag due to lift by a factor of 4 and the wave drag due to volume by a factor of 16. That means lower fuel consumption, a higher range, and smoother flight through the transonic region. Structurally, the benefits were equally striking. A conventional variable sweep wing needs two pivot joints, both carrying huge bending and torsional loads. An oblique wing requires only one, primarily loaded in tension, as the attacking forces are naturally balanced by the oblique geometry. With the center of gravity staying almost fixed during rotation, there is also no need for complex trim systems or shifting fuel loads to maintain balance. And because lift and mass are distributed more evenly along the fuselage, even the aircraft's sonic boom would be gentler, spreading the shockwaves over a longer distance and reducing the intensity on the ground. To test the theory, NASA built a small experimental aircraft, the AD-1 Oblique Wing Demonstrator. First flown in 1979, it looked like no other plane. One wing pivoted across the fuselage, transforming it from symmetrical to diagonal in mid-air. Over the next 3 years, the AD-1 completed 36 successful flights. At low sweep angles, the aircraft handled predictably. As the wing rotated past 45 degrees, however, the aerodynamics became more complex. Pilots reported cross-coupling effects, meaning that a pitch input also caused roll, and a roll input produced yaw. To maintain straight and level flight at a 60-degree sweep angle and about 260 km/h, pilots had to hold roughly 1 degree of yaw, and 7 degrees of bank. It was controllable but not easy. Stall behavior also differed from conventional aircrafts. Normally for swept wings, the air travels from the root to the tip of the wing. This is a problem, as the ailerons, which are responsible for the control of the roll momentum of the plane, are also located at the tip of the wing. If a stall occurs, we therefore lose roll control. Now for the oblique configuration, the forward-facing portion of the wing tends to stall near its root, while the backward swept side stalls near the tip. This asymmetric stall caused a sudden loss of lift on one side, reducing a roll motion that further complicated control. In practice, the rearward-facing part of the wing stalled before the forward-facing part. At the same time, the maneuverability on the rearward side is lost. Yet, despite its challenges, the 81 proved something remarkable. The concept worked. The aircraft remained stable, efficient, and structurally sound. Its performance validated Jones's predictions and demonstrated that Asymmetry could, in fact, fly. Compared to the variable sweep designs of its era, the Oblique Wing offered profound advantages. It achieved the same aerodynamic adaptability with a simpler, lighter mechanism. The single pivot meant lower weight and maintenance, constant center of gravity improved stability, and the smoother area distribution reduced both drag and sonic boom intensity. In theory, an oblique wing aircraft could take off in shorter distances, climb more efficiently, and cruise supersonically using less fuel. A dream for environmentally conscious aviation. But challenges remained. The unusual control coupling demanded advanced flight computers, which didn't yet exist in the early 1980s. Human pilots alone couldn't easily compensate for the complex interactions between pitch, roll, and yaw. Modern fly-by-wire systems, however, could solve that today, automatically adjusting control surfaces to maintain stable flight. But in the end, despite of all theoretical and practical up and downsides of the oblique configuration, one issue remained with the 81. Its speed maxed out at about 320 km per hour, far below transonic speeds where the main benefits could have been observed. Hence, in 1984, NASA and the US Navy were set out to develop a new oblique fighter jet based on the award F-8 Crusader. But due to a lack of funding, the project never even took off and was ultimately cancelled in 1987. Today, the oblique wing remains an intriguing but unrealized concept, one that continues to inspire aerodynamicists around the world. With the rise of digital flight controls, lightweight composites, and the renewed search for efficient supersonic transport, its time may yet come. Still, the aerospace industry tends to be conservative. New designs are expensive, and unless an idea promises overwhelming advantages, it's difficult to justify the investment. Imagine a future airliner that adapts its shape in flight. A craft capable of crossing oceans at supersonic speed while taking off and landing as quietly and efficiently as a conventional jet. A plane that breaks the rule of symmetry to achieve a higher form of balance. The oblique wing challenges our sense of what an aircraft should look like, and reminds us that sometimes progress means letting go of perfection. In nature, symmetry may be beautiful, but in engineering, the symmetry might just be the key to the next great leap in flight.